here's an introductory problem on work. The problem was this, that you have some kind of ramp at an angle theta and height h. And you are pushing with some horizontal force an object up that ramp, and the ramp is frictionless. The object has mass m. And the question is, what is the work that you do getting it from the bottom to the top? Notice that I have to specify that. Work isn't something that just occurs in an instant, it's something that happens over a path. It's something that happens to an object over a path. Well, what I need here is I need the component of the path that is along the direction of the force. So I notice that tangent of theta is equal to h over that thing that I want. Let's just call it question mark, actually. That's fine. And so that means that the length that I want is h times cotangent theta. So the work that's done is the force times the component of the path that's parallel to the force, h cotangent theta. The other way we could have done this problem is we could have taken the path and done that work is the force as a vector dotted with the path as a vector, which would be the force times the path times cosine of the angle between them. Now, if the path is up the ramp, that means that the path is going to be, let's use sine. So the path is going to be h times sine of theta. Nope, other way around. The path is h divided by m. So used to finding components of vectors, sine theta is h over that path. And so the path is h over sine theta. And the angle between the path and the force is, well, theta. So that's cosine theta, which is just f h cotangent theta, which is in fact the same thing we got before. Okay, so we have the first thing, f h cotangent theta. Now, what if we do the problem again, and this time it's the same problem, the same ramp of height h and angle theta, and it's actually the same force on the same object, but this time the object goes from point A at the top to point B at the bottom. So we realize now that in the first problem we went from initial to final, top to bottom, and now we're going from initial to final, which means we're going down the ramp, which means now that there's negative work. This is like a cosine of phi, where phi is 180 degrees. So now the work that's done is minus fh cotangent of theta. Okay, for what's left then on this problem, we're going to use the work energy theorem. And the work energy theorem says that the total work that's done is equal to the change in the kinetic energy. So if we start wondering about gravity, we realize that the total work is the work done by the force plus the work done by gravity. There's no work done by the normal force because there's no component of the path that is parallel to the normal force. Okay, so let's just write in our answers up here. So if we have the box moving down the ramp, that means that the work done is negative FH cotangent theta. It says if the force results in the box moving with constant speed, oh, well, in that case, constant speed just means then that the change in the kinetic energy is 0. So the work total is 0. So the work that's done by gravity is just negative the work that's done by my pushing force. So it's minus FH cotangent theta in the first case and positive FH cotangent theta in the second case. Wow. And then it says if the box starts to slide from rest and is allowed to slide down the ramp without the force, find the kinetic energy of the box at the bottom of the ramp. Well, gravity doesn't know that you stopped pushing. So the work that's done by gravity, actually has to be the same. So the change in kinetic energy has to just be the work done by gravity. The change, oh, this is a fun pen, in the kinetic energy is just the work done by gravity, which is apparently just FH cotangent theta. And if you're thinking to yourself, what the heck is going on in this problem? Is everything just FH cotangent theta? Think about this for a while. Think about what we're saying here, and then stay tuned, because we're going to start talking about the work done by gravity, and we're going to use this result in the next problem. I love this pen. All right, stay tuned.